No, I'll do it from this side.
Here's the second one.
Yeah, no, I understand. Well, thank you. I just put this all up just to say that the work I'm going to show is really the result of collaboration with all these people. Let me use that.
Well, just point it away.
Oh, I see. And all these other institutions. And actually, in the context of this meeting, I realized that I decided to focus on results. So I'm not actually going to show a single apparatus figure. But going back to the session this morning and some of what we heard, I'm really going to try to give an overview of what I think the issues are in atmospheric aerosols, using different mass spectrometers in particular as detectors. How does this work now? This arrow? Okay. And I'm going to start with this slide, which is the overview slide of submicron aerosol measured with our aerosol mass spectrometer all over the northern hemisphere. And if you look at the colors, red is sulfate, blue is nitrate, and there are various shades of green that are organics. And I'm not going to go through this in detail, except the fact that, as was noted earlier, particularly in Rennie's talk, these pie charts actually look very similar almost everywhere. And that's the result. And I'll come back to this, but I'll note that in this particular slide, this point right here, which is from Beijing, is the record highest loading. It's an average in this study of 80 micrograms per cubic meter. But the real point, which I'm going to come back to at the end, and what's missing here, by the way, are any measurements at this point in India underneath this panel, in South Asia besides China. But the real point about, to summarize all this, is that you can argue that the global aerosol is roughly half inorganic and half organic, where the inorganic is actually dominated by sulfate. But what's more interesting here is that the oxygen to carbon ratio, the oxygen content in the organic is on the order of 0.7 on average. And in fact, if you're in remote areas, that oxygen to carbon ratio can actually get larger. And a simple point is that the AMS, I'll just note in passing, is uniquely able to measure all this chemical composition with time resolution of minutes or even seconds, depending on what you're doing. Oh, I gotta get the right arrow. But the real point of that high oxygen to carbon ratio, I'm going to argue, is that the aerosol is overwhelmingly secondary. And once you get away from, for example, primary sources like highways. And in fact, this is a study we did in Mexico City in 2006, I think, where we actually parked our mobile laboratory overlooking the city on a mountain and watched the aerosol and the ozone, or the ox, which is actually the sum of ozone and NO2, increase during the day. Mexico City is a unique place in that when the air is coming from the south, it's on top of a plateau in a relatively clean region. So you can have very clean air, low in ozone and low in secondary organic aerosol. This is really OOA, is oxidized organic aerosol. Very clean air in the morning, and this is the evolution of the air during the day on a time scale of about 12 hours. And there are very few other places where you can see this. The same process is happening everywhere. It's just that you start out at much higher levels. And what you see here is that in this case, the organic aerosol is dominated, is photochemically produced by the same process as producing ozone. It's just saying, and in Mexico City, most of the organic aerosol is secondary in character. And in that context, you should note that the sulfate and the nitrate are also secondary. And in this particular case, this is plume. This is a biomass burning plume, and you can see that it was separate from this. There was no ozone produced in that plume, but it just stands out. So that you've seen this slide in a slightly different form, but the issue has always been how much of the aerosol is primary and how much is secondary. And what I'm trying to say is the secondary organic on a global scale is just a dominant process. The interesting thing, there were two exceptions to that. One is biomass burning, which I'm not going to say anything about, which is also a really big issue. But the other part about the primary organic, as we heard earlier, if you're worried about health, the only place the primary organic is important is next to the sources, next to the highway. But it happens to be where the people are. So if you're worried about health effects, these aerosols are really important. If you're worried about atmospheric aerosol, and I'm going to talk about climate change, it's the secondary that is most important. All these processes where, I'm emphasizing organic here, but that's also just as true for the nitrate and the sulfate. Most of the aerosol, even the inorganic aerosol, is almost all secondary also. The difference here, though, and you've heard this in various ways already, is that we're worried about sulfate, which is the most important single molecule in the atmosphere, in the aerosol. You're really talking about one chemical system, which we actually understand pretty well. SO2 being oxidized to sulfuric acid is pretty well understood. The other important source is actually dimethyl sulfide, but most of the dimethyl sulfide is actually first oxidized to SO2, so that we understand that. On the other hand, VOCs being oxygenated organic aerosol is thousands of compounds. And what we've managed to do with our aerosol mass spectrometer is, I mean, we think we get a good measure of the total OOA, the total organic aerosol, and some information about its elemental content, in particular oxygen to carbon ratio. But what we've really done is simplify the classification of all those many organic compounds. But it turns out that if we really want to do what we call source apportionment, really want to understand where the aerosol is coming from, particularly the organic aerosol, we actually need more molecular information. And that has led us and others to shift towards chemical ionization mass spectrometry, which for us, this is now working in Helsinki, actually started by looking at atmospheric ions. And these particular mass spectra are using a time-of-flight mass spectrometer with what we call an API interface, an atmospheric pressure interface, to directly sample the ions in the air. This is actually work that Fred Isley did 30 years ago. He had a quadrupole mass spectrometer, and we have a TOF with enough resolution that we can see the whole spectrum. We have enough resolution so that we can actually get elemental compositions of most of these peaks. And in particular, during the daytime, this is actually taken in Hutila, which is a research station in a boreal forest in central Finland. During a nucleation event, during a banana that you heard about, we actually see sulfuric acid clusters. And we even see sulfuric acid clusters with some ammonia in them. And so that in this case, we believe the actual nucleation event is largely controlled by sulfuric acid clusters, small ones. On the other hand, at night, we see a completely different mass spectrum, and in particular see these peaks that are labeled in green at masses over 250 and even above 500. And it turns out that these are ions of C10, H14, and it's actually O9 is the neutral molecule that actually clustered with a nitrate anion. But the remarkable thing, and I should mention in this environment, alpha-pinene is the major biogenic emission, which happens to be C10H16. But what's amazing is I'm seeing molecules, neutral molecules, with 9 oxygens attached to 10 carbons in the gas phase. This is a gas phase measurement. And no one would have believed these molecules existed if we didn't have a detector that showed them. And they're also there during the day, but in the atmospheric ions, the sulfate dominates. So we shifted from this simple atmospheric ion measurement and converted this into a nitrate SIMS, also a la what Fred Isley did a while ago, but again connected to the top. And then and moved to the lab, and in a number of studies that culminated in this paper by Mikhail and Kolstakin and the group of Thomas Mentel and Eulish, we were able to show that if you mix alpha pinene with ozone, just simply alpha pinene and ozone, you make all these molecules that have this incredible number of oxygens in them. I mean, 11 oxygen attacks 10 carbons. In this experiment, we very clearly showed that if you add seed aerosol, all of these species start condensing on the seed aerosol. They all want to go into the particle phase, and in fact, we know now that this LVOC, which is extremely low volatility, what we call extremely low volatility organic carbons, we see this O to C greater than 0.7 in the gas phase, C10 and C20 molecules, and we know now, I'm not going to show, maybe I'll show some at the end, that they participate in nucleation and cluster and nanoparticle growth. But more interesting to me is that, and that's why we were trying to understand nanoparticle nucleation and nanoparticle growth during the bananas and hugula. But the real point is we found a major source of secondary organic aerosol. The thing to note, just like the sulfate, these things have low volatility that compares with the low volatility of sulfate. But just as with sulfate, most of these molecules end up in the accumulation mode of the aerosol. We actually have found a source, a direct source of highly oxidized organic, which really changes the picture of how secondary organic aerosol is made. If I go to this slide, what's going on here, it's really an auto-oxidation mechanism where you form an alkyl radical that adds an oxygen, and then internally, an alkoxy radical. That alkoxy radical then abstracts a hydrogen to form a hydroperoxide that forms another alkyl radical that then can add another O2. And what's really going on is we can add 4 O2s, 4 oxygen molecules to one molecule in a minute or two in the atmosphere. And it turns out that, so you can add up to 4 oxygen molecules under specifically low NOx conditions really quickly. And in fact, this low NOx constraint is actually we're finding out it's not that low. And in fact, now we've done a lot of studies on a lot of biogenics, and we and others, and it turns out this is a really common process. So that we're making these highly oxidized organics very quickly, so that we can make a picture like this, where if I try to look at the overall particle formation process going from nanometer particles up to CCN, cloud condensation nuclei in the order of 100 nanometers, the nucleation process is some combination of sulfate and maybe some bases and use ELVOC. But even at the larger particles, and at least in a natural, unpolluted environment like the boreal forest in Finland, this LVOC is a major part of the process. And then if I shift gears a little bit, it turns out, so that the issue. So this is maybe representative of what I'm going to call the natural atmosphere. But in terms of understanding effective aerosols and climate, it turns out we also have to understand the pre-industrial atmosphere. And there's this paper by Ken Carslaw that came out in Nature a couple of years ago that pointed out that for the current climate models predicting the effect of aerosols on anthropogenic radiative impacts, that the pre-industrial atmosphere, what he called the natural aerosol, is just as important as the current atmosphere. So that if you look at the standard IPCC diagram that says that the negative blue bars that are due to direct and indirect aerosol and aerosol cloud effects that reduce the net radiative forcing due to the greenhouse gases. By definition, all these bars are a model calculation of 2000 or 2010 minus the atmosphere in 1750. And there's been almost no real thought put into what did aerosol and clouds look like in 1750. We don't have, there are no proxies for aerosols or clouds, to say the least, so that to put this in another perspective, the reason that aerosols are so difficult to understand and in the atmosphere is that, for example, I can put up this diagram comparing the concentration of the greenhouse gases and various other species, but in particular, we're talking about the greenhouse gas warming. Greenhouse gas warming is determined by the evolution of gases, stable gases at the parts per million ratio, where the perturbations in the aerosol we're talking about on a global basis are in the ppb range. And in order to make quantitative statements about the impact of this aerosol, and the point is that we believe that roughly half of the current global warming has been mitigated by increases in anthropogenic aerosols since World War II in particular. In order to evaluate that, we need to understand the whole aerosol life cycle at this concentration level and how it competes with the greenhouse gases. So to put up this diagram, which has been shown in different form earlier, we really need to understand how nanoparticles become ultrafine particles, become fine particles, and eventually clouds. And we need to know which molecules are controlling the process in the current atmosphere and in the pre-industrial atmosphere, let alone in the future atmosphere. So that with our aerosol mass spectrometer, we measured the chemical composition of the fine particles. We're now using various SIMs, we and other group, to try to understand the composition of the molecules in the small clusters. What's really important here is we're really going from PPT concentrations up to PPB or even ppm in the polluted regions, where a simple point to understand is if you have a PPT of condensable material during the whole day, continuously there, that will accumulate a ppb, roughly a microgram per cubic meter over a day. And in the natural atmosphere, that's the process that both controls nucleation and nanoparticle growth, as well as accumulation of haze and cloud CCN. And I'm going to skip this. And then that totally contrasts with what's going on in Asia right now, and specifically in China. This is the cover of Science magazine 2 weeks before the Olympics in Beijing in 2008. And I can say that, and the whole question was the air going to look like that in Beijing during the Olympics? And in fact, it didn't, partially because they got lucky. The air came from the north and it rained a lot, but they also shut down roughly half of the economic activity. And they actually did that again in Beijing last November for the Pacific Conference, whatever it was, where Obama and a bunch of other people went. APEC. And it was a huge success. They actually showed that indeed, you can control the aerosol or control the pollution if you're willing to turn off the economy. and you laugh, but in China, I'm actually spending more and more time in China. In China, that's not a small lesson. The people need to understand that. But in any case, so this is where I was going to end. The way we have this contrast between, from my point of view, trying to understand climate change and the effect of aerosols on a global basis, and then we have to deal with, as Rennie pointed out, we dealt with this 40 years ago. In fact, to add to what Rennie said, the issue in China is they managed to create this on a time scale, 2 or 3 times as fast as we did. Now the question is, can they fix it on a time scale 2 or 3 times as fast as we did? But anyway, I was going to end here, but Rick said I have to show this. So this is now, because this is my other favorite topic. This is the 26 cubic meter stainless steel, ultra clean steel, polished stainless steel chamber at CERN in Switzerland, where that happens to be sitting next to this accelerator right here, so that we are able to shoot a beam, a meter squared beam of pions to simulate cosmic rays. But from my perspective, what we really do is they turn this whole chamber into the source for a chemical ionization mass spectrometer. So we get to make ions throughout that chamber, and in particular look at the clusters in the nucleation, so that we see mass spectra like this. This is what called the mass defect diagram, but what's important here is that if we put in sulfuric acid and ammonia, we see the appearance of sulfuric acid ammonia clusters. If we put in dimethylamine, we see the appearance of dimethylamine clusters. If we put in organics, it's actually pinene diol, which is a surrogate for alpha pinene oxidation product. We see clusters, in this case, of sulfuric acid and organics. And what's important here is at the same time, we measure the nucleation and the nanoparticle growth. That correlates exactly with the formation of these clusters. And in this context, my favorite slide, and this is actually under similar conditions, this is what we see in the boreal forest in Himlet, in Hutula, where these are sulfuric acid clusters with ammonia, and we also see the organics. But the part that I'm most proud of, or is most amazing to me, is that we can time resolve the appearance of all those clusters. In the cloud experiment, we control this by turning on the lights, which controls the formation of sulfuric acid from OH oxidation. And in this case, where we're looking at organics plus sulfuric acid, what you can see here is these are the appearance times of each one of these bands of clusters, where these are tens of molecules, of molecular ions that we're detecting, maybe more than tens. And you can see that we can time resolve them on a time scale of minutes. I mean, this is the same process that was in Perdeen's burner, not the same process, a similar process. The difference is that in this case, it's happening over a half an hour. We're actually watching the collision rate of these big molecules, these LVOC molecules and sulfuric acid. We're measuring it directly in a time scale of minutes. And we can connect this directly, in this case, to the nucleation rate. Under these conditions, the nucleation rate's all kinetic. It's really just controlled by how quickly these molecules can collide and grow. And then I'm going to end on this slide, where the real point here is that we're talking here about nanoparticles growing, clusters growing to nanoparticles, and then to slightly larger nanoparticles, and keep growing, where at the same time you have this competition between all of these molecules, clusters and molecules and small nanoparticles, colliding with the condensation sink. And it actually turns out that, for example, the growth process is the most important. But my overall point is it turns out that sulfuric acid and highly oxidized organics formed in the gas phase through auto-oxidation. We believe this auto-oxidation mechanism is actually really general for many different organics. It's that photochemical gas phase process and the competition between all this aerosol microphysics and the growth of the condensation sink that controls the aerosol life cycle. And if you want to go back to the natural atmosphere, where we don't have any direct measurements or proxies, until we quantitatively understand the chemistry and kinetics of this process, we will not be able to predict what the exact aerosol loading and even CCN was in the past, let alone also the future. So to say it one last time, the real point of this meeting, in the context of atmosphere at least, is you cannot reduce this process to a scalar. The reason aerosol and aerosol measurements in theory, whatever, are so difficult is that inherently, it's this process or equivalent processes that we just cannot reduce to PM 2.5. To put it simply, that scalar just is not going to tell us how the aerosols are really being formed and what role they play in the atmosphere.